Hello, everyone, and thank you for having me. My name is Arkadiusz Guziński, and today I will be discussing the application of artificial intelligence in the characterization of bacteriophages. I am a bioinformatics team leader at Proteome Pharmaceuticals, where with my team, we are focusing on the analysis of the bacteriophages and the bacterial sequences. Additionally, I also represent the company PhageEU, which is a spin-off of Proteome, where with team we developed the platform dedicated to advancing phage research using AI tools. Our platform is designed to accelerate all the analysis, and I will show you a little bit more later about this platform. So, okay, to begin, let's talk about the rapid growth in bacteriophages science, which is driven mostly, I think, by popularization of sequencing technology, which is now much cheaper than 10 years ago. In the last decade, the number of complete phage sequences available in the public databases has increased significantly, currently around 2,400 or 3,000 even. New sequences are added each year to the public databases. Of course, new data always open the new opportunities for research, particularly in the therapeutic application, what is the most interesting for us. But it also presents the challenges in managing, analyzing, or annotating these datasets. This is why the AI usually take part and speed up the research. Also, you can see on the pictures, I also checked the number of publications in the databases that combine keywords bacteriophage and artificial intelligence or machine learning. And here too, there is a noticeable increase. Even while preparing this presentation, I discovered new publication describing new programs and algorithms. So it is hard to keep up with the new reports on this issue. So it is really developing really fast right now. So maybe I will tell you what the artificial intelligence is. At its core, AI refers to the use of the machine and algorithms to simulate human intelligence, like thinking, learning, and decision making. So this is an umbrella term under which cover a variety of fields, including machine learning, which is a subfield of that enables computers to learn from the data and improve over time. So this is a kind of algorithms that we use. And of course, machine learning can be also further divided, and we have different types of ML. I am just putting here the three, I think, the most common and the most popular types of machine learning. First one is supervised learning, where models learn from the labeled datasets. And as an example, if we're trying to distinguish a dog from the wolf on photos, first a human must mark a large batch of photos and feed these models with them that it can learn the patterns and later recognize the dog from the wolf. So we have to do some work and we have to prepare the data first. In contrast, we have the unsupervised learning. There is a which we allow the model to learn the patterns itself. So we don't have to put efforts in this or a lot of efforts. The third quite popular method is the reinforcement learning, and where the model receives the feedback on its classification, and usually made also by human. After receiving this positive or negative feedback, the relearning process take place. In this way, after several iteration, model start learning better and have better predictions or classifications. So you can use those kind of analysis to extract information from biological data. So we also, when it comes to the phage research, AI can be extremely helpful. particularly in therapeutic applications. One of my key focuses is ensuring that phages are safe and effective for therapeutic use, which means I have to deeply characterize them at the genomic level. This begins with identify the phage sequences. Sometimes it can be challenging task due to the presence of the host DNA, or you have problems because you are working on the metagenomic data. This is why some tools are showing up, like Deep Viewfinder, Marver, or VirSorter, which help you to filter and identify the phage from the metagenomic data. So it's really speed up the process of filtrating these sequences. Another crucial area, which actually is my specialty, is where the AI plays an important role, is the prediction of the phage life cycle. Understand whether a phage follows a lytic, lysogenic, or chronic cycle is essential, especially for the therapeutic purposes, where virulent phages are preferred. This is because we usually expect quite rapid effects in therapy. The lysogenic cycle assumes the integration of temperate phages with the bacterial genome, and initiation of the lytic cycle is delayed. What means the bacteria is still alive and still harms the patient. So we don't want these life cycles. This is also the case with the chronic cycle, which practically does not lead to the death of the bacteria. So we are focusing only on the lytic cycle and strictly virulent phages. Traditional methods of annotating phages genomes are actually time-consuming. We have developed pipelines that involve a lot of softwares, and it is time-consuming to gather all the information and take something interesting from these outputs. This is why we developed the PhageEI. Right now, the PhageEI is a platform that automates this process. Of course, we are not the only ones that create such programs, but we are trying to create an entire platform useful for from the point of view of the phage research. So here you can see how the PhageEI looks like. And we constantly improving our platform to offer more comprehensive tools for phage analysis. With each month, we scrap public phage databases, analyze all the sequences, and update our repository with the key information, such as taxonomy, life cycle prediction, similar phages. You can also do it by yourself. You can put there your sequences, and you will receive all the information also. Recently, we improved our classification models by shifting from nucleotide-based to protein-based, and we implement the deep learning process. That leads us to the better confidence score, which we are achieved with this model, and you can see on the left picture. Also, what is very important, we introduce explainability to our model, which is mostly now focuses on the integrases or other proteins that involves starting the lysogenic life cycle. And this is really important and desirable for us because right now we know that our model reflects the process that we are also perform manually. So it is great information for us. Also, what is important, so if we have we identify the sequence, we know the life cycle of phages. Also, it's important to know how the virion looks like. Also, In this, we are using the protein structure predictions, and in this area, the AlphaFold is the have the most impact in that field. AlphaFold allows us to model phage proteins in silico with remarkable accuracy, which is critical for understanding how phages interact with bacterial hosts. This knowledge actually is crucial for designing phage therapies that target specific bacteria, and hopefully it will make phage host interaction models more precise. And to give you the information how important it was, the impact this tool has had is best demonstrated by the Nobel Prize in chemistry, which Hasabin and Jumper, along with Baker, were awarded for this work. Although 2024 actually is a bit of AI year, because in physics also awarded a prize for its contribution to the development of artificial neural networks. Okay, so I also mentioned about the phage host interaction predictions, and I think this is the most one of the biggest challenge we face today. And we are facing the prediction of phage host interaction at the strain level. While we have made great strides in prediction interactions at the genus or species level, like you can see on the table from the review on the right, we have a lot of great tools that predict the taxonomy level of the host on the genus or species. But achieving strain level specificity remains quite elusive. This limitation is largely due to a lack of experimental data and comprehensive databases. Moreover, phage host interactions involve more than just binding to receptors, because it involves bacterial defense mechanisms such as CRISPR-Cas or restriction modification systems that often come into play, making the prediction process even more complex. This is right now most of the people and the researchers, as I look at the publication, is struggling with developing such a model. Okay, that was actually really fast, but I wanted to take you to the journey where you can see how much we already do with AI in the phage research. So to conclude, we are only at the beginning of this journey, but AI has already accelerated bacteriophage research in many ways, and still is much work to be done. Mostly improving phage host interactions models and improving the specificity of predictions. For me, is a missing puzzle to fully show the potential in composition of phage cocktails. But when we will achieve this, I believe that in near future we will see major advancements in this field, with AI playing a central role in developing personalized phage therapies. And at the end, I also encourage you to read the publication of Pirans, which is extra bibliography here, because he predicts how the phage therapy will looks like in the next decade, and I really hope he was right about his predictions. So thank you very much. That's all from me, and I am open for questions.